Hello everyone. Temporal contextual recommendation in real time was announced as the best paper in the Applied Data Science track in CUKDD 2020, which was held August last year. My name is Hongin Lee, and in this video presentation, we'll walk through the key components of this research paper, which was written by several researchers in AWS AI Labs. It was accepted in Applied Data Science track that address real-world problems that is already or could be possibly deployed in near future. And the recommender model introduced in this work is named the HRNN Meta, and it achieved a state-of-the-art performance on various datasets and is currently available in AWS personalized service. The contents of this paper start with the terminology and the research goals, related works, covers methods, experiments, and conclusions. For the terminology, a recommendation system delivers a personalized experience based on the customer's preferences. So it's, for example, it's like specific product recommendations, like YouTube, or customized direct marketing, or the content for emails, or re-ranking of search results. It is often costly, so the large companies like AWS offers a black box recommendation system. It is not for end users, it's actually for developers to add individualized recommendation service in their application. No heavy engineering is required, so any developers can easily use one. The real-time personalization in recommendation system improves recommendation in real time by leveraging the capture live events feeds from user's current session. So it uses like click histories or browsing histories, or like device information, whether user is on mobile or desktop. And they blend this data with existing data to improve its predictions. The research goals of this work, the research questions that I think started this work is two. One is how to efficiently train recommender systems with many items, and how to copy its how to copy its the recommender building recommender systems with items that is changing in its popularities. So the research goals are written into 5 series of lines. This work proposes a black box recommender system that adapts in real time and learn from long user histories. So it has to like overcome long-term dependency problem of RMNs, and it has to address the cold start scenario problems. That means that the prior interaction histories are non-existing, and it has to be scalable, and it has to debias some item popularity trends in order to faithfully predict the future. The solution that this work is presenting is named as HRNN Meta model that leverages introduced HRNN model, also leveraging metadata info. And it also proposed the importance sampling, IS, and item trend corrections, ITC, as additional solutions to address the problem. The solutions, I think, is explicitly designed to adapt to a diverse set of scenarios, such as the real-time cold start when users, accidentally click an ad or don't click any ads because it was just a random video on a web page, or like when the date set for the recommendation is like continually updated. And for the evaluation of these solutions, they test on real-world data sets, and they do numerous synthetic experiments on to prove their effectiveness in the research goals, and they already actually deployed in production at scale. So I think it is quite evaluated thoroughly. The related work. I will start with introducing the collaborative filtering. Most recommendation system is based on the user and item interaction. When there is a user, there could be a lot of items that is interacted with interacted by user. By this I mean they click or do something about that item. They say good or bad or something like that. And there are two methods: content-based filtering and collaborative filtering. But what they they have this in common, that they use these patterns in the user item interaction matrix, and then they decompose the matrix into some way of utilizing that info. But I think the remedy is that they are not in real time, because they cannot be responsive to life changes, because they have this single giant matrix that is representing the whole general information. Of course, there could be other methods, but it is written like this in the paper. And to address the real-time problem in recommendation system, HRNN was introduced. I think it was around about 15 years, 2015. It's basically hierarchical RNNs that are proposed to model user sessions in real time. It used two levels of GRUs to learn session level and user level representations. So let's say there is a user here, and the user might click the link to this watch web page, or for shopping or something, and he may choose another and another again, but then he takes a break and he starts another session of internet browsing or eye shopping for women's shoes. Then at an arbitrary time, the recommendation has to recommend something, but it has to be grounded on the last session, not the prior one, the prior one. So in order to do that, HRNN keeps two levels of GRUs, one that goes straight like globally for that specific user, and another level is the session level GRUs. They are initialized at the start of the session, and they are terminated at the end of the session. and they just are used to update the user level GRUs that is globally updated. The architecture of HRNN is first start it's initialized with the session level representation initialization. It has to somehow get the input data at each time step, and it has to encode in a recurrent neural network way, and when the session ends, it has to update the user level GRUs, and using this updated user level representation, when the break is over and another session is initialized, the session level has to also be initialized. Session level GRUs, I mean, has to be initialized by the user level representation, or we could do it like this, that using this global representation, we could edit, we could inject it to each and every step of this time step of this session level representation. And in order to train these RNNs, typically backpropagation through time is used for each session level and user level GRUs. And when using these mini batches of multiple users, all user events has to be backpropagated concurrently. HRNN for a recommendation system is not different from the HGRUs that I talked. It's just a general term. And when you formulated the input data format, given a user history as denoted as X, each interaction, each interacted items is written in the attributes and its associated value. The attributes is written in one-hot embedding. This is typically like the name of an attribute, let's say click or device info or something like that, and the value may varies according to this attribute's name. And the recommendation system use this RNN output that represent the recommendations scores converted into the probability by using softmax. And for given item, all the probability for the model to output the item as the recommended item for that given specific time can be written as this. And the HRNN meta is presented in this work. This is the overview. It looks quite confusing, but it's not actually. It uses HRNN. It's like baseline that improves real-time problem, and it has time delta controls, feedback encoding, and item features decoding, and FFM that solves scalability and cold start and contextualization. I'll introduce each key components. The time delta controls encodes time information. You could just think of this TK as timestamp, and session control signals, CK, at the input features. So the input features was originally A and V, and T and C is also concatenated. And that's it. But to improve the model performance and computational efficiency, it actually tries to compact the recurrent neural network into little smaller size. I'm not so sure about how do they reset these GRUs, because they were very not clear about. But I think it's just means resetting the GRUs. But anyway, they claims that it improves the model performance, or at least to show the comparable performance, and also improves computational efficiency in both memories and the throughput of this model. And they claim that it improves architectural compatibility, which means that instead of using GRUs, they can use LSTMs or other transformers or something like that, some other RNN models as a base of this HRNN meta, base model of this HRNN meta. They use this control signal to efficiently run this algorithm, but each HGRU, this means that the user level, this refers the user level HRNNs, and this GRU refers session level RNNs that was mentioned earlier, and they think that it can be replaced with other models, but they didn't mention the result. The feedback encoding, it's simple. They use some extra info, basically like contextual info, as a metadata. They can they also like basically concatenate this user feedback info into info features. It includes like user features such as ages, dynamic features such as device, or feedback events such as purchase or costs of that item. They say it improves it improves model response to implicit negatives. By negatives, I mean since as a I mean the no click. What I'm saying is that when I'm saying positives, it means user clicked on item, and by negatives, I mean the user did not. And the implicit negatives means that unintentional negatives, such as like refreshing without any clicks, or just short dwell, random visit on web pages. They say this metadata can like improve the response to these implicit negatives. Item feature decodings. The item feature decoding is of course in the decoding phase, and it has it actually computes two set of scores. One that is done by standard standard way, but the other is done by like a peculiar way. I'm not sure about how to interpret these equations, but I'm guessing this might be working as an identity like function, decoder as an identity function, like to like explicitly supervise that when this score is high, this score has to be low, and when this score is high, vice versa. So the lambda, the hyperparameter, actually, the random value lambda is working as like a dropout that in training time to randomly choose between these scores, and when this score is high, this score has to be low. So I think they build this the mirror function of this standard decoder, using just weights and biases for hidden representation in RNN. But I think the FJ in here is basically the same as the HK, and they are probably something like going when they are multiplied, it'll always be like 1. I'm not so sure about this, but I think it is something like explicit supervision for supervision, yeah. And they say it is very useful for cold start scenarios. The FFM is short name for field-aware factorization machines. This, I think, is a method of the data pre-processing for recommendation system. Standard way is factorization machines. When given a raw input data for recommender system, every field has one latent features, such as this feature and value. But in FFM, it is not. It for per every field, several latent features might be existing. For example, given a field of publisher, it could be actually this might be easier. For given field of gender, the feature is male, but it can be also female. And in FFM, they formulate this gender that represent the field, and the G female that interconnects these fields and feature name and its value. I'm a little confusing about this FFM, but I looked for the some examples of this FFM and found this link that it basically builds indices for indices for fields and each interconnected features, and it uses tuples to represent a feature, and it improves the contextualization of the raw input features. They claim is what they say. The importance actually we already walked through the key components of HRN and meta, and another additional solution this work presents is importance sampling. It keeps the computational complexity efficient during training by approximating the loss only on the sampled subset of data, the entire data. How they do it is that they formulate the loss as a policy optimization problem that aims to maximize rewards. By rewards, I mean the positive clicks. So if you write the loss it's actually the log softmax. This is softmax and log cross entropy loss between. This represent the scores, so the scores of given by the, output by the decoder, and its true labels, which in this case is rewards. And by leveraging negative sampling to approximate loss, we can formulate like different, more efficient way of getting approximating the loss between positive sample and negative samples. The loss can be written as this. This represents the scores for the positive samples in a random pair of positive samples, and this represents the scores for negative samples in random pair of the sample data set. And that loss can be also revised as into this form, given that assuming that the distribution Q is already known QJ is should represent the frequency of an item AJ. AJ user access the frequency or user access the item AJ. So you can get the scores, and we can easily compute this frequency, and we can just use this loss to compute to approximate the loss. When you're using, we have to calculate this loss for the entire data set, but we don't have to do it in this form, so it's very computationally efficient. Item trend corrections is also known as ITC. It divides the fast-changing item trends. So it divides trends. By trends, I mean the popularity or the exposure rate or the frequency of an item appears to users. It is different from the click-through rate because the click-through rate represents the probability of an item is clicked, given that the item is already exposed to the user. And in recommendation system, they don't trust this item exposure rate because it varies from time to time, so it is not reliable data. They want to remove this bias, so they want to figure out these values, the exposure rate. It is the unknown term in these equations that has to be solved out. It is obtained by item trend decomposition that separates out the click rate, the left term here, and the exposure rate, the right term here in this equation. We can obtain this value, the approximated value, from the scores, and we can obtain this click rate because it doesn't really change, I think. In the papers, they say it can be obtained from global click-through rate in the last training. So we can obtain these two terms, and we can obtain this term, and we add this the bias term to the score, and to remove the item exposure bias for specific item. So and after that, they somehow retrain this model, but it is not clearly stated. I will introduce the experiments. There are like total of 9 experiments. I cannot state everything. I will just briefly say 7 of them. I will introduce the research question and how the what the test experiments are doing, and introduce the data set name, show the figure, baseline, and interpretation here. Thus, adding metadata to the input improves the model performance. In order to answer that research question, they test model performance with or without adding metadata to the input. So on the movie lens data, is real world, is 20 million interaction. It's very large. They try to test adding metadata. This is adding the input feature decoding, and this is adding user features and the feedback encoding. And the metric is perplexity. The lower the better. And as you can see here, the 2 lines that improve the performance in perplexity from its baseline. So from the MLP is improving, and from the binary RNN, HRNN meta is improving its perplexity. So yes, metadata is useful. Long-term dependencies. Does HRNN leaves vanishing gradients problems, and thus allowing models to have longer memories. They suggest qualitative example of a recommendation for a virtual user who watched the following movies, the 5 movies here, with the genres specified. And they see if the consistent recommendation is possible after some time passed. So the genres of this movie is usually about comedy and drama. And after the delta t, the time stamp, as time goes by, the recommendation has to be grounded to this comedy and drama, and it actually did. And they can't really show some quantitative experiments, but they claim that HRM meta has learned to place some weights on temporal inputs and maybe relieve long-term dependencies. And in RNN and HRNN meta, they compare HRNN meta itself to its baseline. So the first question is hierarchies in RNNs useful for recommendation system? They compare HRNN with time delta controls and input feature decoding. I denoted as HRNN plus here, against other baseline models, GRU and HRNN. This is the thing, the HRNN that was mentioned in related works, and POP and BPR. As you can see, the higher better, and is showing good performance, but it's slightly low. But they claim that this proposed method, it shows 10 times faster throughput computationally than the baseline. So they also introduced the feedback encoding. Is feedback encoding useful for encoding contextual info? They compare HRNN with feedback encoding against other contextual encoding methods such as factorization, machine, and or other things. They presented the results from 2 datasets, and as you can see, when using HRNN, when actually using feedback encoding, lowers the error. The lower the better, so this is good. But when when we are not using this feedback encoding, the performance is not good. So they conclude that feedback encoding is actually very useful for encoding contextual info. And for the cold start scenario experiment, they simulate cold start scenario from benchmark data set by randomly selecting half of the all items and evaluating the recommendation performance only on that half selected items. And their baseline is called random choice, and compared to the baseline, it outperforms, and proving that the HRN meta is very effective in cold start scenarios. The importance sampling, does IS importance sampling improve the computational efficiency? They compare the performance and throughput of the HRM model with and or without importance sampling on various large-scale datasets. As you can see, there are several datasets that increase in scales as you go right, and the IS is the baseline, not the baseline, the proposed method that is HRNN with importance sampling. Actually, this is incorrect. HRNN meta with importance sampling, and the density refers to HRNN meta without importance sampling. And as you can see, this represents memories, and it shows great difference in memories as well as in the throughput, but IS is showing better results in PPL. No, actually, density is density is showing PPL great result in PPL. So yeah, we can formally say that IS is very good and greatly improve the computational efficiency. And for the item trend corrections, does ITC improve recommendation performance and stabilize the learning when item trends are changing? They test model performance with real-world data set that has changes in the item trends. I mean, the item popularity trends. And they use this Outbrain data set. I think it is a data set that is designed to like evaluate the trend invariance of these recommendation models. And the blue line represents our model, and the baseline is the sort, I think is like state-of-art baseline, and the yellow line, the green line refers using HRNN meta without ITC. So it shows great difference, and it also outperforms the baseline. So we can conclude that ITC is very effective against the trend invariance. So the conclusion: HRNN meta solves all. I mean, it first addressed these 5 research goals and the key components of HRNN meta that are in total 5, and as well as these 2 additional solutions, they solve somehow related to these goals. But my review on this work is that I want to just know how to efficiently build metadata for cold start scenarios for graph neural networks, because it's really using the metadata it's remarkable. Yes, thank you for the listening, and thank you.